if you can move the disks 1 second with 64 towers of Hanoi, okay, it will take, let me make sure I got this right, 19,025,875,190.2 centuries. Now, you might say to yourself, these monks, they're so slow, 1 move a second, come on. I have a computer, I can make 1,000,000 moves a second. 1,000,000. So now I'm going to divide this by what? Divided by 1,000,000, right? Now, we have reduced this to 19,000 centuries. If I make 1,000,000 moves a second, right? 1,000,000 moves per second is 1 per second, 19,000 centuries. So you can see the monks maybe not have been that far off. It's possible, right? We don't quite know what the result is. But here's what I want you to remember. Suppose that I'm solving the towers of Hanoi, and n is equal to 8. And I can solve it in time t. And now what I do is I get a computer, so this is 1x computer, now I get a double speed computer. And I want you to tell me how big a problem can I solve in time t when I double the speed of the computer. That's a good guess. Anybody else? No, it doesn't depend. Well, when n was 8, that means I executed 255, or roughly 256 instructions. So therefore, n is equal to 8, and t of n is equal roughly to 256 in time t. Now, t of n is roughly equals to 512 in time t because the computer has doubled speed. What's the function? It goes from here to here, here to here, here to here. So what's my answer? 9. This is exactly the example I gave you before. I doubled the speed of my computer and my problem size increased by 1. Okay, and the reason for that is because when the problem size, when exponential growth increases by 1, the instructions count doubles. Well, instruction count doubling is a double speed computer. So a double speed computer goes 1 higher. Tell me what is the complexity of the function of an algorithm when I get a computer 3 times faster, the problem increases by 1.
4.
What's the complexity of an algorithm when I get a computer 3 times as fast? I can only solve a problem 1 more than that.
Like the 3x.
3 to the n power. 3
to the n.
It's an exponential complexity, 3 to the n. Because, so this is a little bit different. So if you have here n, and then you have 3 to the n, if you have 3, what's that? 27, right? It gets hard. What's the next one going to be? 3 to the 4th, 60. 81. Okay, so you see what's going on here is if this is the size of the problem, this is the instruction count for this kind of algorithm. So therefore, what's happening is this is 3 times. This is 3 times. So if I get a computer that can execute this 3 times this instruction at the same time t, the problem size will increase. So the function is its exponential. So this is an exponential function. going from the problem size to the complexity, from the complexity to the problem size. It's the inverse of the exponential function, which is the logarithmic function. So the logarithmic function and the exponential functions are inverses of each other. For example, if I have, let's say, 2 to the nth power, that's a value. Okay? But if I take the log base 2 of 2 to the nth power, now, you know, some of you are a little bit rusty on your math. We're gonna review so that everybody will be much more confident, because I find that some people come here who are very strong in math. Sometimes they get very confused by this course because they always took math where they knew what they had to do. But this is a math where you have to figure out what to do. So you know all the skills, you know all the math. It's a matter of being able to apply it. So we'll need to study some interesting parts of algorithms. Algorithms are broken up into 3 areas of analysis. And 2 of them are kind of interesting, and 1 of them is extremely interesting. Basically, algorithms behave differently for different inputs. Even sometimes we have the same size input, the algorithm complexity is different. Well, that's not really true. The algorithm complexity is the same, but the performance is different. So for example, I run a problem, an algorithm, with an input of this size, and it runs in 12 seconds. I run it with the same input size, it runs with 18 seconds on the same machine, same load. I run it again, it runs in 2 seconds. What's going on? Same algorithm. But the data is different. Same amount of data, but different configuration of data. So algorithms are also sensitive to not only the size of the data, but the nature of the data. So therefore, we have 3 cases of algorithm analysis. One of them is the best case, with size n problem, worst case, with size n problem, and of course, the average case. Which one do you think is the most difficult? Yeah, average, because nobody really knows what it is. What is an average? You know? We think we know what an average. Well, you take the worst and the best, put it in between, divide by 2. No, doesn't work that way. Not always. Okay, because the average basically has to take into consideration all the possibilities and weigh them evenly, and maybe most of the possibilities are up here in a bad area and very few are in a good area. Or maybe most of them are in a good area, very few are in a bad area. So the average complexity might not be the average of the worst and the best. So what the heck is it? So sometimes we have to really think about that. So we need some statistical thinking, some hypothetical thinking. We'll do all that kind of stuff. All right, does anybody have any questions? What can you ask, right? What can you ask an algorithm course on the first day? All right, so today is what? Today is Wednesday? All right, so next class is Monday. Okay, very good. So that's it. Have a good weekend. Thursday, Friday, Saturday. All right.